In this chapter, we're going to study exponential and logarithmic functions. First, we're going to evaluate exponential functions. We're going to graph them, and then we're going to graph functions with base e, which is your natural base. And then we're going to use compound interest formulas. The exponential function f with base b is defined by f of x equals b to the x, or y equals b to the x. Remember that f of x and y mean the same thing. In this case, b has to be a positive number that is not 1, but it's got to be bigger than 0, and x is any real number. So your exponent has to be any real number. Now, here's an example of why we might want to evaluate an exponential function, and we'll go ahead and evaluate this one. The exponential function f of x is equal to 42.2 times 1.56 to the x models the average amount spent, f of x, in dollars at a shopping mall after x hours. What's the average amount spent to the nearest dollar after 3 hours at a shopping mall? So we're going to substitute 3 for x and then evaluate our function. So we're finding f of 3, which is equal to 42.2 times 1.56 to the third power. And we're going to approximate. And since we're talking money here, when we plug this into the calculator, we're going to get approximately 160.21. You might as well round it to the nearest cent, since we are talking about money. Now, if we want to graph an exponential function, we really need to make a table to kind of see what the function does. And we need some negative numbers, zero's good to put in, and some positive numbers. So we're going to plot these. But first we need to figure out what f is at negative 2. And that's going to be our y-coordinate of our point. So 3 to the negative 2. Remember, when we have negative exponents, that means we have the reciprocal. We're looking at the reciprocal. That's 1 over 3 squared, or 1/9. Now, if we take f at negative 1, we've got 3 to the negative 1, which again is a reciprocal, 1 over 3 to the first power, which is just 1 over 3, or 1/3. Now, f at 0, anytime we take a non-zero number and we raise it to the 0 power, we get 1 for an answer. So f at 0 is just 1. And f at 1 is equal to 3 to the first power, which is just 3. So now we want to plot those points. Now at negative 2, we have 1/9, which is really hard for me to graph properly. It's really close to our y-axis. And negative 1 is at 1/3, which is just a little bit higher above the y-axis. And 0 is at 1. That's one that's a little bit easier to graph there. And then at 1, it's all the way up at 3. And if we continued on at 2, 3 to the second power, 3 squared, is all the way up at 9. So go over to the right 2 and up 1, 2, 3, 4, 5, 6, 7, 8, 9. And about there. So you can see how this function is looking. This is what your exponential function looks like. And this is what most exponential functions look like. They have this shape that they may rise faster than that, but that is the standard shape for your exponential function. And since any non-zero number to the 0 power is 1, they're all going to cross at that 0, 1. And here is another graph of that so that you can see a little bit better where these points are and where the horizontal asymptote is. Now if we're going to graph 3 to the x minus 1, Remember, when we subtract just from the x, or add just to the x, that's going to be a horizontal shift. And it's kind of backwards from what we're used to. Usually when we add, we go to the right. When we subtract, we go to the left. So this one is x minus 1. So we are going to shift everything to the right. Horizontal shifts are a little bit backwards. Shift it to the right 1. So you can see all these points are just shifted horizontally to the right 1 space. And the one in red is our new one. See the transformations? They show up over and over, and it doesn't matter what kind of function that we have, what kind of graph that we have, the transformations still work the same. Here's some of your characteristics of exponential functions. In this form, f of x is equal to b to the x. Your domain is always going to be all real numbers. An interval notation that looks like negative infinity to positive infinity, because you can use any real number for your exponent, and that's where your x is. And your range is going to be all positive real numbers, and an interval notation that looks like 0 to infinity. The graphs of these functions pass through 0, 1, like I mentioned before, because anytime you raise a non-zero number to the 0 power, then you get 1 for an answer. So your y-intercept is 1, and there's not an x-intercept. If your number that you are raising to different powers is greater than 1, then you've got a graph that looks like the one in blue that goes up from left to right. And if the number that you're raising to different powers is a proper fraction, in other words, it's between 0 and 1, then you're going to have the function that you see graphed here in red. And there are going to be one-to-one functions that have inverses, and as the graph of b to the x approaches but doesn't touch the x-axis. So it's got y equals 0 for a horizontal asymptote. E is defined here as the value that 1 plus 1 over n to the nth power approaches as n gets bigger and bigger. So if you plugged in larger and larger n's into this, then you would get closer and closer to this value of E. And it's approximately 2.72. It's called the natural base. Here's an exponential function that uses E, our natural base, that models the gray wolf population of the western Great Lakes. And X in this function stands for the years after 1978. So we're going to project the gray wolf's population in the recovery area in 2012. So first of all, we need to figure out how many years it's been since 1978 from 2012. So just subtract. And once you've done that, we need to figure out, we're going to take this number and we're going to plug it in for our x value into the equation and figure out what the population should look like. So, we're looking for f of 34. Again, on your calculator, you're going to plug this in. You should find, if you have a scientific calculator, you will have an E on it. You also have natural log on it, and we'll use those later. But for now, we want to be able to find that E and use that. If you don't have it, you can use 2.72 to approximate that. And we're just going to put the 34 in there and multiply it by the 0.042 for our exponent, and we're going to approximate whatever we get from our calculator. Now I'm going to round this to the nearest whole because this stands for a gray wolf population. So we're not going to get a half of a wolf or any portion of a wolf, whole wolves only. So that's approximately 4,445 wolves. Now here are your formulas for compound interest. And the T in both of these formulas stands for your time. R is going to be your rate. We also have another variable in the first one, n, and that's going to be our compounding periods per year. So if we compound twice a year, that n is going to be 2. If we compound quarterly, that's going to be a 4, because there are 4 quarters there. Or if we compound monthly, then the n is going to be 12. So I hope you get the idea with that. Okay, so we're going to start with $10,000. We're going to invest at an annual rate of 8%. And we're going to find the balance in the account after 5 years subject to quarterly compounding. Since we don't have continually compounding interest, we're going to use the first formula, since we know the number of times that we're going to compound our interest. The other formula is when you have continuous compounding, and that's a different formula altogether. So for this one, we need to know what our principal is. That's the money that we start with. So we've got our $10,000. And then we're going to replace all of the variables that we can and then solve. And in this case, we've got all the variables. Later, we'll learn how to solve this for one of the other variables, one of them that is an exponent. But for now, we're just plugging these numbers in and finding our. So again, we're going to change our rate into a decimal. And the n is the number of times that we compound, which is quarterly. And then the n again shows up as an exponent. And the time is 5 years. So really all you have to do is make sure you put everything in its correct place and then evaluate with your calculator. The amount we'll have after that is approximately So, again, just replacing variables with things that you know and evaluating with your calculator. This is the total amount, not just the interest. So here's the exact same problem, except we have continuous compounding. The last question, we had compounding quarterly, so only 4 times a year. This is continuous. So we should get a slightly different number. You may want to look into that, see if you think it will be a much larger number or not. So let's check. We start out with our $10,000, but in this case we have a different formula. We're going to use our natural base and we're going to raise it to the interest rate as a decimal times the time in years. And then let's see. Stick that in your calculator and we will approximate. In this case, we get 14,918 and 25 cents. Which is a little bit more than what we got in the last problem where we compounded only quarterly. So, this is your lesson on exponential functions.